I want to mention a little bit more about models. So the exponential model is just using the diode equation. ID equals IS e to the VD over VT for most of the region in forward. And this is really hard for us to solve this equation, even for the simple circuit. If we give it one set of conditions, yeah, we can solve it. So for instance, we can write two equations with two unknowns. We could write the diode equation as one of our equations, and then we can look at the circuit and we can do KVL around it. So we have the current has to equal, so the voltage drop here, and the voltage drop here, and the voltage drop here, those all have to sum up to 0. VDD equals IDRD plus VD. So we can solve for ID. That would be VDD minus VD over R. And we could work back and forth with these two equations. There's various ways we could solve those. We could just do an iterative approach, for instance, just make a guess, then guess for the other, and go back and forth. And after 2 or 3 rounds, there's an example in the book, after 2 or 3 times, you should converge pretty well in a solution. So it's not that hard, but you know, it's going to take you 10, 15 minutes just to solve it for one condition. So this is really the exponential model is something that I'll have you solve for a set of conditions, right? What's the current with the scale current of this at a temperature of such and such a voltage? So I'll have you solve it once when I give you all the everything except you find one number. But other than that, to really solve a circuit, that's a lot of work. If you did these two equations, the diode equation and then this KVL kind of equation, you could draw 2 lines. If you know enough information, you can draw for the diode. And if you know the resistance, you could draw and the voltage it's applied, you could draw a line that represents what's happening in the resistor, and you'd have an intersection which is VDD over R, and you'd have another one which is just VDD, and the slope of this line would be 1 over R, and this line is called a load line. And if you plot both the exponential plot and the load line on the same plot, then you can see that there's an intersection. And that intersection is called an operating point. That's where that circuit would operate. And so we could solve it and understand the operating point for this. It's controlled by equation and by KVL, by those two equations, and we would get there's only one solution. There's only one possible solution that makes any sense. And that's when I was in school, professors, you know, the teachers are always, you know, 20, 30, 40 years older, and they learn from people 20, 30, 40 years older than them. And so you could tell that all the professors were in love with this method, and they wanted us to use it and wanted us to understand it. And in that era, you know, if you were in the lab with an oscilloscope, you had a Polaroid camera, you'd go up and put it up and go click, and take a picture of the Polaroid camera, and then you could get your ruler out and draw a load line on your Polaroid camera and solve it and stuff, and your Polaroid picture. And yeah, it works. It's exact. It's not bad. It's not too hard. But the only really reason I even bring it up right now is I want you to realize that there are 2 equations, and there does have to be one operating point. And you could solve it, but do that. But that load line concept, it gets referenced, it gets brought up. Another model is the constant voltage drop model. That's where we just say that the diode turns on at, say, 0.7 volts. And for any voltage less than 0.7, instead of having this curvy thing, we say it's at zero current. And for any positive voltage, we just say it's a short at 0.7 volts. So it looks like this, but a short at 0.7 volts means it's not really a short, it's more like a battery. So the on situation is, we say we got 0.7 volts across the diode, and we replace it, instead of really with a short, we replace it with a battery, or you could say we replace it with a short in series with a battery. And when it's off, the battery might still be there, but it's an open. And this model is pretty easy to use. It's very similar to the ideal diode model, which was just the ideal diode model, of course. I have to put something on because it doesn't do action using my diode model. Just has it turning on at 0 volts, right? And the constant voltage drop model has it turning on at 0.7 volts. And so, boy, I wish I knew why I can get it to magnify. I wish I knew how to get the dumb little pointer to come up consistently too. So the difference is, does it turn on at 0.7 volts or does it turn on at 0 volts? And it's not very hard to do that 0.7. Now, one thing that's important, so if I took this circuit here, if we take this circuit and use this, solve this with a constant voltage drop model, so we have a voltage source, a resistor, and a diode all in series in a loop. If we solve it with a constant voltage drop model, in the off situation, it has no current in any negative voltage. So that's exactly the same as the ideal diode model. But in the on situation, we replace the diode with a battery, and then we can solve it. But this isn't a real battery, right? So this is not the kind of battery that can generate power, right? It can't generate any current. It just has a voltage there. So that voltage is there and existing there to allow you to solve KVL correctly, right? You can add up the voltages. You can add up the voltage here and here and here and find the current knowing this resistance, right? You know the voltage drop here, here, and here. But this is not a voltage source that's going to make power the way this is a voltage source. So it's, by saying it's a battery, that's a little bit kind of confusing, and I don't think we have a model that we normally use that's like this. It's kind of an odd thing. So it's not a real battery. Well, current goes through it. If we used a capacitor, then it would work dynamically correctly, but it wouldn't. This will handle DC. DC is just fine. So it's a little bit of a kind of a weird amalgam of some concepts, but if you just understand that the ideal diode model has a 0.7 voltage drop, 0.7 volt voltage drop for the diode, and you put it in with the high side to the low side facing the same way as the diode current flows, then you could solve this for I is VDD minus VD over R, or 5 minus 0.7 over 1,000 ohms. In this case, gives us 4.3 milliamps. And before we did the ideal diode model, which would be VDD minus 0 over R, gave us 5 milliamps. So that's not that different of an answer. But to get this answer, all you have to do is subtract 0.7 from 5 volts. It's not a whole lot of extra effort to subtract that voltage drop. And by doing that, you get an answer which is actually quite a bit closer to the real answer. So the real answer that we had by the exponential model okay. The exponential model's answer was I is equal to, where did it go? 4.262 milliamps. Jeez. This cheesy $5 pencil is pretty bad. It doesn't really work. much better on the computer monitor either. I know if I write slowly enough, it's pretty good. So 4.262 milliamps is pretty similar to 4.3 milliamps. It's remarkably close. In fact, that's something like a 1% error, as opposed to more like a 10% error between these two, or between these two. So just putting 0.7 volts in for the drop of the diode and solving it, you come pretty close to the right answer. It's amazing. Yeah. This word right here that's totally illegible. I don't know what's wrong with you people. I hesitated to write it because I knew it was a lot of letters, and I probably can't do it. Well, let me do it this way. Let me just write this. Still not much better, is it? So if we solve the diode equation, we get 4.262 milliamps for this exact same diode, whatever that scale current is. It's remarkably close to the constant voltage drop model. And so it's a really simple model, but it's really, really common for people, including me, to say, well, you just assume the diode's on and say it's 0.7 volts for a silicon diode. In general, if you're trying to find whether a diode is simply on or off, if, for instance, you want to know, is the LED lit up? If you've got a circuit with a bunch of LEDs and you want to find out, is the LED actually lit up? The ideal diode model will probably be fine. It'll work really well. You can use the constant voltage drop model for that to get a little bit more precise answer. But as long as you really just want, kind of digital levels sort of thing, the ideal diode model would be great. And if you're trying to find current, the constant voltage drop model is almost always going to be good enough for you, unless I've basically indicated I want a more exact answer. But often you can use that. And just remember that a silicon diode has a drop of 7 volts, and a germanium diode is about 0.3 volts, and a Schottky diode is about 0.25 volts. And with that, you can work a lot of stuff out. LEDs are different, so they're made out of gallium arsenide and aluminum gallium arsenide and a whole bunch of other materials. So LEDs, their constant voltage model drop may be more like a volt, even 1 1/4 volts, something like that. There's a lot of differences with LEDs, but they're fundamentally the same thing. Okay. So I mentioned before, and I'm going to mention just slightly more detail now, but we'll talk about it a little bit more later. Reverse breakdown. So the real curve for diode is this exponential forward current, I equals e to the VD over VT, and -1 for very close to 0. And then in the negative region, there's essentially no current, or the current is minus IS, minus the scale current is the only current in this reverse region. But if you apply a large enough reverse voltage, and it's different for every kind of diode, every diode made, if you apply a large enough reverse voltage, they will break down. And when we say breakdown, it doesn't mean a catastrophic failure. It means that current increases very, very rapidly, and it becomes more and more negative for a very small change in voltage. Here we have this exponential increase, which is a huge increase in current for a small change, but this is an even more sharp increase in voltage. Um, and there's a couple of ways that this can happen. And usually both is happening at the same time in any one device, and it's sort of a mix of them, but you can tailor a device to have one kind of breakdown or the other, and there's a little bit different characteristics. So one is avalanche breakdown, and that's where you have, say, a minority carrier. If we had a depletion region here, and you had a I've just got that. Well, this is what's going to happen. Yeah, this is the right way. This is an N-type region, and the minority carriers are holes. And if we had a hole in the depletion region for some reason, and actually holes don't have to wander into the depletion region. They're made by magic everywhere in the semiconductor, just by thermal energy. And so holes will get created in the depletion region once in a while. And once you have a hole there, it feels a tremendously strong negative voltage on the other side of the depletion region, and it'll be accelerated across. And as that hole is accelerated across, it can get a lot of energy. Acceleration, the longer you keep accelerating it, the higher its energy becomes, right? And it'll go faster and faster and faster, and it'll get more and more energy. And so if you've got a large voltage across here, you've got a large field, and that can accelerate it a lot. Usually that wouldn't be just the depletion. It's not just the depletion built-in voltage that's going to do it. It's a large part of it is due to a large negative voltage. But if we have a large enough negative voltage we've applied to this depletion region, the carriers, for instance holes, are accelerated very rapidly to the other side of the depletion region. And as they get accelerated and move faster and faster, sometimes they're going to hit a innocent silicon atom that was just hanging out there, just minding its business, being good. And when this hole hits that silicon atom, it'll make an electron-hole pair. And the electron will get accelerated this way, making some current, and the hole will get accelerated this way, and we'll now have two holes traveling this way. So when this hole hits a silicon atom, an unionized silicon atom, it'll ionize it, creating an electron in a hole, and we'll get like twice the amount of current, or 30%, 70% more current, something like that, 66% more current. We'll get a bunch more current from that one collision. And if we have a huge field, then all those carriers get accelerated, and they'll go on and hit some more innocent silicon atoms, create some more carriers, and we get more and more current that avalanches or multiplies out very rapidly. But it only happens for a large negative field. And this is really out of scale. Usually this would be kind of like this, and then come way out to here before it comes down. So it's usually a very, very negative voltage compared to this positive voltage here.
How negative, if you have a rough idea?
Sorry, was there a question?
Yeah, I was just asking sort of like what order of magnitude of a negative voltage are we thinking about here?
Minus 5, 10, 20, 50, 100, 200. It varies by the device. So you can build a device on purpose to have a very high resistance to reverse breakdown. By physically having a very wide device, it'll be able to absorb voltage. But it's generally a relatively large voltage compared to this. You can't see there it is. Compared to this 0.7 volts is at least 6-7 times larger. Yeah. So the question is, does it damage it? No, it doesn't damage it unless the current becomes so large that it melts something. So if you tried to apply a voltage over here, you would have this huge current. And if you didn't have any resistor in your circuit or some other means of limiting current, the current would skyrocket. You'd have many, many amps, hundreds, tens of thousands, millions of amps trying to run through this diode. And well before you even hit an amp, you would melt a bond wire, usually a solder ball, a bond wire, something like that would usually melt, and then poof, your diode's dead. So but the avalanche process itself is not destructive. And there's one other way that you can get a lot of carriers in there and a large reverse current, and it happens roughly the same sort of voltage, is just because of that large field, we've got so much energy applied to that device in there that you start to break silicon-silicon covalent bonds. So if you break a covalent bond, it's the same as making an intrinsic carrier. When you break a covalent bond, you make an electron-hole pair, and they fly off in opposite directions, and you get a bunch more current. And so the more and more voltage you apply, the more and more covalent bonds you break, and the more current you get. And it happens very suddenly because there's a characteristic energy for most of these covalent bonds. When you hit that voltage, they all start breaking down, and you get this massive current right away. And that's the Zener effect. And there's usually a combination of the Zener effect and the avalanche effect. So you can imagine if you've broken a covalent bond and made an electron-hole pair and accelerate them, it's very possible that those electrons and holes are going to bump into some silicon atoms and knock off some more carriers. So there's usually a mix of those, and you can actually kind of figure out what that mix is, but we're not too worried about that, or I'm not going to worry about it. Because this drops so sharply, especially Zener diodes, and Zener diodes depend on the doping and the size and shape of that whole device. We can make Zener diodes with very well-defined breakdown voltages. The avalanche effect isn't quite as consistent, but the Zener effect is very consistent, and we can make devices that have very consistent, repeatable breakdown voltages. So they make good voltage references. The only problem with them is they tend to be 5, 6, 7, 8, 9, 10 volts, 20, 30, 40 volts, something like that. And with such large voltages, compared to where modern electronics work around 1 volt, it's sort of it's useless to have a 5-volt voltage reference when your circuit can't handle more than a volt, right? So they're not as widespread use as they used to be. But still, if you're looking at a system that's got, like this computer that's got a 20-volt power or battery on it, well, not this one, but if you've got a laptop that may have a 20-volt battery on it, then you could make very good use of a Zener diode as a reference. Now, if you zoom in on this breakdown region right here, then you could see there's something more like this. And we've got a curve, and it's got a slope. I've shown it as just dropping straight down. It really does drop really precipitously, but you could still measure a slope there. And if we extrapolate that slope to where it intersects, there would be a minus VZ naught. There would also be a voltage, VZK, the knee voltage, where the current starts deviating significantly from the scale current. And we could, most usefully, we could pick some current and call that a test current or a reference current. And then we could know the voltage level that we get at that current. So that would be useful if you were designing a reference current. A reference, you could say at minus 5 milliamps, you get a voltage of minus 4.8 volts. And that would exactly determine this point on the operating curve. And it wouldn't mean that that point there, it wouldn't mean that you have to operate it at those conditions, but it gives you a condition that you can then use and to understand others, and you might operate it here or down here or wherever, but you would know, you could work out how it works from that. So we have one more really useful model to talk about. That's the small signal model. The small signal model isn't maybe so useful for diodes, but it's stunningly useful for amplifiers, and that's where we're headed to in the last part of the class, is working with amplifiers and transistors. So, and we in fact can analyze diodes with the small signal model, and if we were building a real signal system, there are diodes in it, and we would be using the diode small signal model to analyze it. So it's worth it to introduce what's going on here, and it's a little bit easier to understand the small signal model in the case of a diode. But you might say, this doesn't seem very useful. But rest assured, it's an enormous effort saver when we get to transistors. So what are we talking about? We're talking about, for instance, in this curve here, And remember, I said you could keep zooming in on this. It's exponential. As much as you zoom in, it always looks the same, right? It always has that same characteristic shape. So you could zoom in anywhere on it. And just like calculus, you could find the slope of that point right there, call it point Q, and you could find a tangent there, the slope of that. And at that point, at that tangent, we know that there's a curve, which is y equals mx plus b, and that's really easy to use compared to the diode equation with that exponential in it, which is hard to use. And the thing is that this linear equation, y equals mx plus b, is only going to work over a small region. That's why we call it a small signal model. So it might be, 0.8 volts out here, and this might only be good in a region of, plus minus a few millivolts. But if your signal is a few millivolts, then this is tremendously easy to use. And in fact, that's a really common situation, to have just a few millivolt kind of signal level. So remember, there's this system. A big letter with a big subscript is a DC voltage. That's a voltage that doesn't change. I also call that a bias. And if we have a big letter with two big subscripts, that's a DC supply. VDD, VCC, VSS, VEE. Those are all bias voltages that we apply, and they're expected not to change. They're DC. And we could have a DC diode current, some current that doesn't change, that's constant. And then we could talk about a composite signal. And so, or sorry, I should say the AC part of that would be little letter, little subscript, right? Little v, little d is a function of time. That's an AC or a small signal. So we could make this composite little v, big D. That would be the composite signal, which is a function of time, and it's the DC signal plus the AC signal. We've just broken them apart. We have DC plus AC, and we can represent that by the letters and the subscripts, kind of confusingly, and it's a little bit hard for me to always be able to write that clearly, because there's sometimes the I's look like L's, look like 1's, and you can't tell what is that. I1, sometimes it looks like 1, 1, you don't know. You can't tell the difference between a little v and a big V necessarily. If it's kind of written normally, it looks the same, so I always try to write it looking more like a little nu here. That's the way I write this. I write my V's as kind of a little nu. But then that looks like voltage or frequency in other situations, which is kind of confusing. So I just know that this is what I write when I'm writing, dealing with signals in electronics, that I'm writing it with these kinds of letters. So anyway, we've got the diode equation, and I could write it in terms of this composite signal. So little I, big D is a function of T. That's a composite current. That's a composite current. Little I, big D is big I, big D plus little I, little d, right? That's the DC and the AC. That's the composite current. Would be IS. IS is a DC value, so it's a big I, big S. It's a constant value. It's a tiny value, but it's a constant, right? Times the exponent e to the VD. So this is little v, big D is a function of T. That's the one I put in there. So I just use these two composites over VT. And VT, again, is a DC value, right? Big V, big T is how I try to write it, the thermal voltage at room temperature 0.0258 volts. So I could write it that way. And then I could expand this. So I've got this current would be IS e to the, since little v, big D is the same as big V, big D, little v, little d, I could write it that way, right? Big V, big D plus little v, little d, DC plus AC over VT. And in an exponent, is the same as multiplication, so I could separate these. So I have IS e to the VD over VT. This is all DC, right? This is constant. Oh, that's a constant. And we would recognize that constant must be big I, big D, right? Big I, big D would be a constant diode voltage, a DC constant diode voltage, times e to the little v d of t over vt. And this is the AC signal. So then I would have little I, big D is equal to the DC current, ID, big I, big D, times e to the little d is a function of t over vt. And this t and that t, this is time, this is temperature. It's hopelessly confusing, but hopefully that makes sense. We've got a constant DC and an AC part, but I said that what we really want is this composite to be DC plus AC, and I've got them multiplied here, so it's not quite the form that we might want. But there's an approximation. We can expand E to something as a series and truncate it after just one time, and it works pretty well. And so e to the little d over vt, if e over 1, this is 25.8 millivolts. So if this number up here is really small, like 345 millivolts, then 5 millivolts divided by 25 millivolts is like 0.2, and that's a small number. That's much less than 1. And that's small enough that this approximation works. So e to the Vd over Vt is 1 plus Vd over Vt. Then we have I times 1 plus Vd over Vt, and multiply it through. We've got a DC part, which is ID times 1, and then we have an AC part, which is big I over Vt times little vd as a function of t. And this is valid as long as little vd over Vt is small. We have a DC bias plus an AC signal. And if you look at this, just that small signal part, little I, little d, as a function of t, is, I should have that as a function of t right there, big ID over big Vt. Those are both constants. The DC current, ID, divided by a thermal voltage is a constant. And that's a amp per volt, which is an inverse of a resistance, right? Resistance is volts per amp. So this is like a resistance, the inverse of a resistance. And we could say that there's a resistance here, which is the thermal voltage Vt divided by the current running through it, the DC current running through that diode, Rd. We call it Rd. And that's a little r, little d. So that's a small signal resistance is what that is. It's not a resistance the way you're used to a resistor. It's a resistance from the viewpoint of a small signal, right? From the viewpoint of this little Vd of t and little Id of t, this is a resistance. By Ohm's law, that's a resistance, right? It's not a resistance from the for the DC part. So it's not like a DC resistance of these IDs and VDs. It's a small signal resistance, and we'll come up with this concept a lot more. But if we're only dealing with small signals, then we use it just like a resistor, and we can replace that diode with a resistor as long as we're in this small region where we know the resistance. So this should make sense. I versus V, we've got this plot that looks like that, right? And the slope of that should be 1 over resistance. It's an amp per volt, right? So that's 1 over resistance. So the slope anywhere we're looking at is a 1 over resistance. And depending on the voltage and current DC levels that we picked for Q, we get a different value of RD. RD depends on ID, right? little rd, the small signal resistance, depends on the current we're running through it. And for a small current, we get a huge resistance, and for a massive current, we get a tiny resistance. Hopefully I said that right. So what good is this? Well, it means if we were only looking at the small signal, right? If we had a, instead of looking at this, I should have written that as a little I there. Instead of looking at a, and you can't tell, oh, is that a big O or a small O, right? So there's real problems with this nomenclature. But anyway, if we're trying to find this output voltage as a function of a small signal voltage, which is just a plus or minus few millivolts, we could find that by replacing this diode with a resistor with a value of RD, and then we have a really easy equation to solve. Much easier than the exponential model, right? But it's only valid for those small signals. The good thing is that inside of almost all our electronics, signals are almost always small. It's much easier to use because circuits, we can linearize circuits because of this kind of small signal approximation. It actually means that a circuit is linear for very small signals. So almost all the signals in a circuit that aren't digital are very small signals, a few millivolts, microvolts, like that. And we can use those small signals to make our radio amplifiers and radio receivers and A to Ds and D to As and all those other linear circuits. We can make all those work with small signals. So what would an analysis look like? And I'll bring this up again when we're talking with amplifiers, but you should get an idea right now. The general scheme for solving a circuit would be first you do a DC analysis of whatever the circuit is, and you find big VD, big ID, VT, and you solve the circuit so that you know the voltage, the DC voltage, and the DC current in that circuit. And once you have that, then you can calculate little rd, the small signal resistance, and then you replace the diode with a small signal resistor and solve the signal for the circuit for just small signal. And then at the end, if you really need to, you can combine the currents and voltages, the DC and the AC part, to get again the total solution. But lots of times we're just interested in the small signal solution. So what's this mean? So we could use a string of diodes as a voltage regulator or reference. We'll call it a regulator. So each one has about a 0.7 voltage drop, 0.7 volt drop on it, right? And we've got a 1K resistor here, and then we've got this this voltage. We've got ground down here. We've got a voltage source up here. We have 10 volts plus or minus 5 millivolts. It's maybe just on the large side. Maybe I should call it a little smaller, but anyway, it should still work. This might be noise, right? We're supposed to have 5 or 10 volts. It's supposed to be a constant DC 10 volts. It's supposed to be VDD, right? Big V, big DD. But actually, it's plus a little V sub n, little n of T, noise, right? Some noise voltage. And it's varying plus or minus 5 millivolts. So we assume that we've got a 0.7 volt drop DC on each of these diodes. So then the voltage, the DC voltage right here would be 0.7 plus 0.7 plus 0.7, or 2.1 volts here, DC. And that's supposed to be steady, right? But it's actually plus or minus something due to this 5 millivolts. So we could then find RD as VT over ID, because we can find ID, knowing the voltage here and the voltage here. We can find ID is 10 minus V out, or 10 minus 2.1 over 1K. So we've got 7.9 over 1K, or 7.9 milliamps. So there's 7.9 milliamps. Excuse me. Okay. 7.9 milliamps flowing through here. I don't have any output load. We've got 7.9 milliamps flowing through all of this. They're all in series. And that means that we've got a RD, which is VT over that 7.9 milliamps. So we've got 0.0258 volts VT divided by 0.0079. That's 3.27 ohms. So from the standpoint of a small signal, it's as if we have a 3.7 ohm resistor for each of these diodes. And we put those in. Now it's an easy circuit to solve, right? It's a really easy circuit to solve for that small signal. So V out is just a voltage divider. We've got these three resistors in series, 3 times 3.27, divided by 3 times 3.27. I didn't draw that right. Plus 1,000. I catch things in my sometimes I write things correctly, even though I don't write them correctly in my notes. So if we work that divider times 0.005, because we were plus or minus 5 millivolts, right? So we now have a 5 millivolt signal, a small signal. Multiply that out. We get 9.81 over 1,000, 9.81 times 0.005. We get 4.86 microvolts. So that means as far as that output goes, the output voltage, it's going to be 2.1 volts plus 48.6 microvolts. So that original signal was 10 plus 5 millivolts, plus or minus 5 millivolts, and we've come down to here, and we've got a regulated voltage, which is more consistent. Instead of having the variation of millivolts, we've got a variation of 50 microvolts. So we've significantly reduced the variation, and that would be the output signal. And the nice thing is, it's really easy to work this and to understand it. The small signal makes it much easier because we've linearized the circuit. It's much easier to understand what's happening. And it's actually a correct, true analysis. It gives us the right answer as long as that variation really is plus or minus 5 millivolts, as long as it is a small signal. And that's maybe a little bit big, but it's the right idea. I should change that to be 2 millivolts or something. So we've got a reduction in the influence of that noise. And that's a lot easier than solving the exponential model, right? We'd have 3 of those exponential models basically to solve. It's a linear circuit. It's much easier to work. So that circuit really is, so I said we were trying to regulate something. It's a regulator. That's the circuit that I drew right here. This is a regulator. I could draw it slightly differently. If I drew this circuit, God, come on, pointer. If I drew the circuit slightly differently, it's the same thing. It would look like this. We got a voltage source, we go through a resistor, and we go through a diode. In the case the one we just did, we went through 3 diodes. But the function of this diode is to regulate the output voltage to that normal diode drop, about 0.7 volts. That's the DC value we're going to see. And that's different. The circuit we already did was a rectifier, right? So the diode has switched locations, right? We have a diode here, which is rectifying the circuit. The output is only the DC part, or the positive voltage of an AC input. And here we have a circuit which takes the voltage and makes it steady and constant, even though the input is varied. And what this regulator is also saying is if we think about the constant voltage drop model, it's as if we've replaced this diode with a battery, and a battery is a DC source that doesn't change much. That's like what we've done with this diode, and it's just that this diode can't generate any power. but it can support a constant voltage of about 0.7 volts. And any changes that we have in this input here, so this input changes voltage, not any, but a lot of the change in this input voltage, it doesn't show up here. Instead, it shows up as a change in the voltage drop of this resistor. So the current changes through the diode as this voltage changes, and that change in current causes more voltage to drop here and not much voltage change here. That's where the change is occurring. It's occurring in this resistor. Does that make sense? So that other example, we had 3 diodes. We could have 2 diodes in series to make 1.4 volts and various things like that. So in this case, if we have, I said that original solution for a 1K resistor and 5-volt source would be 4.263 milliamps running through this diode, right? That would be the exponential solution. And the constant voltage drop model was 4.3 milliamps, but I said that. And that gives us an output voltage of 0.737 volts. 0.737 volts is the output voltage for a 5-volt source here. If Vn changed by 10%, so if we change this by 10%, V out changes by 0.4%. So that's what we mean by regulator. It's not perfect. There is still going to be variation in this voltage, but if this changes 10%, this changes 0.4%, and this actually, the voltage across the resistor changes by 11%. So most of the change happens here, not here, which is what we want. We want a steady output voltage from a regulator, and a diode is one way to do that. And a couple of definitions that you need to do homework, perhaps, or to know exist, because they come up in specification for power supplies and things like that. You can define line regulation as the change in the output voltage over the source voltage. V plus would be the source voltage, Vn, and that the units there would be millivolts per volt. And load regulation would be the change in the output voltage for change in the load current, and that would be millivolts per milliamp. So you could look at it as a change in the source, how well is your line voltage regulated, or you could look at it for a change in the load, and how well does your voltage regulator regulate the output voltage for a change in the load current. So why would this source, this V plus, which is meant to be the same as Vn, why would that change? So Vn would change. Vn changes, for instance, due to things like noise or loading on other parts of a circuit. So this could change for various reasons. The power supply could get hot. It could get cold. I can't get the pointer to show up at all. It could get hot. It could get cold. All kinds of things could happen. People keep testing positive. Why am I not surprised? So there could be changes on here. It could be due to other parts of the circuit, right? There could be, we've got a certain power coming in here, and someone over in physics drops a wrench on some power supply and it shorts out in our current or voltage sacs, right? So the voltage could change because of things that are completely unrelated to your circuit. You could change the load though, right? You could turn on a whole bunch more transistors, and suddenly you could have a greater demand on the load, and you'd have an increase in current, in which you would be looking at the load regulation. So both of those are valid ways in different ways to look at what's happening. So a power supply, and somewhere about here I like to pick up a power supply and show you a power supply. I need to figure out how to do that for miracles of modern technology people at home. Yeah. That's totally legible. I don't know what's wrong with that. It gets worse the more I draw, doesn't it? So there's a load resistor, or whatever the circuits are, and the current through that load is IL. So a power supply means those wall boards that we all love in the walls, right? You get your little phone charger and you plug it into the wall and you plug your cable in and you start charging your phone. Or you've got a fancy phone that I can't afford with wireless charging, so then you have a charging pad and you plug the charging pad into a little power supply that plugs into the wall. And whatever you're doing, you've got this little thing, a little cube, and that is taking that 120 volt AC power that's coming in from the wall and converting it to a much lower voltage DC that your device can handle. Sometimes those power supplies are little wall warts, and old cheesy bad ones were really heavy. Nice, good, expensive new ones, which is now the norm pretty much, are much lighter because they mostly have electronics, so that's good. You want to have electronics, you don't want to have heavy transformers doing everything. They're much more efficient, and they can drop the power usage to almost zero if they're not being used. So sometimes those power supplies are those little wall boards that you plug into the wall. Sometimes those power supplies are built into this computer. So this computer, it just has a plug that goes right into the 120. So it's got a power supply built into it somewhere. Almost everything, with the exception of motors, and a lot of motors have power supplies also. So a lot of motors, we have variable control of the speed of them. But if you have a motor with fixed speed or really old-fashioned control, it may plug straight into the 120 and use 120. And if you have a heater, it'll plug into the straight 120, like your toaster and those lovely heaters that glow red. Those don't have a power supply. They're just using the AC coming into us. But most of the electronics, virtually all the electronics you deal with, LED light bulbs, these fluorescent light bulbs, they all have power supplies. And a basic power supply is going to look something like this. They don't all have transformers. A transformer does two things for us. Principally, it does more, but principally it does two things. It converts that AC coming off the wall at 120 volts AC, and remember that's like a peak of what, 167 plus or minus. It converts it to a lower voltage, 8 volts, 20 volts, 40 volts, I don't know, whatever, but it converts it to a lower voltage, which is probably safer. Usually that lower voltage is safer, although that's a little bit complex answer about what safe means, but in fact, the answer is not that it's safe because it's a low voltage. Its answer is it's safe because it's a low current that's going to exist. But it converts it to a lower voltage usually, although some cases they convert to a higher voltage. It also isolates us. If we have some fault anywhere in this circuit here, as long as this coil isn't broken, and if we have a fault anywhere in here, if the kid comes up and grabs this end and this end and connects it with a paper clip, there's no way to get 120 volts off of here because we're isolated from this 120 volts on the wall. So power supplies almost always have a transformer in them to make them safer, to isolate us from that 120 volts. That 120 is dangerous. So there's a transformer inside here to make it safe. Now, you're not supposed to open this up, but you're supposed to know that these plugs that we go into the AC and the wire that's going all the way to anything else is dangerous, right? And once you convert it to DC, anything on a small, any of the other electronic cables you're used to, USB and all that, those are low voltage and those are safer and those have been isolated. They've always been isolated. Virtually always, I mean, they just have to be isolated. It's virtually always isolated. If it wasn't isolated, there would be warnings on there. It's not isolated. When you look on the back of a power supply, you'll see those little a straight line with little dots underneath it that says it's DC, and that also, I believe, is supposed to mean it's isolated. That configuration is supposed to mean it's isolated, I believe. Although, don't assume that that is true. I believe that's true. Something else about, oh, so there is cases where we don't expect to have any access to the high voltage AC. So light bulbs, LEDs that plug into that socket, you're not expected to be able to touch the line and neutral on that. And so those don't actually have to have isolation. So something that plugs into it and it's supposed to be plugged into, it's not going into a wall outlet, it's going into a light socket or some fixture like that. Those may not have isolation. So if you break this fluorescent bulb up there, which no one but me can see, if you break that, not only will you be exposed to about 2-3 milligrams of mercury, which is a neurotoxin, but you would have 120 volts between the two ends of that. If you touched it, you'd electrocute yourself. Yeah. If there's a voltage, the question is if there's a voltage drop across each diode, then that's going to reduce the voltage. Yes, it is. 8 volts AC, what is that? That's actually about 9 volts peak to peak, right? 9 point something. It's the square root of 2 in there, right? So these numbers are, this is approximate. We'd go from a transformer normally in any power supply, and the first thing we usually do is rectify it. So we have a big AC signal, and then we have a smaller amplitude AC signal. Then we rectify it, and we get just the positive going pulses. We might get every other one as a half-wave rectifier we already looked at, but there's ways to get all the pulses. So we get it rectified, so it's all positive voltage. Then we'd like to go through a filter, and we'll do this. We'll talk about transformers and we'll talk about filters. A capacitor can help us filter things out, so we'd have much less variation. We'd take this thing that goes all the way down to 0 twice a cycle and make it kind of vary up here. You can't see the wonderful wiggling on my finger very well, but it'd be just wiggling along there. And then we'd like to regulate it and make it a steady voltage. So if we had, for instance, from 0 to 8 volts amplitude here, and then we had 8 volts plus or minus 5 millivolts, then a diode circuit like this regulator could actually get us a pretty well-regulated output voltage of 0.7 volts plus or minus 50 microamps or 50 microvolts or something like that. We'd have a nice, relatively speaking, steady DC voltage that went from the wall all the way to our electronics. Rectifiers. We did the rectifier with the ideal diode model, but actually we do need to use the constant voltage drop model to get a little bit more accurate result. So when it's off, the output is 0 on a rectifier, but when it's on, we really have a 0.7 voltage drop here. And if you look at the plus minus signs, it means our output voltage is going to be reduced by 0.7 volts. So V out is V in minus 0.7. If we used a Schottky diode, it would be V out minus 0.25. And in a lot of circuits, that actually makes a difference in the efficiency. So a lot of circuits, we might use a Schottky diode to get a smaller voltage drop. So that means that this AC input signal, instead of being this ideal signal, is actually 0.7 volts everywhere, 0.7 volts less than the ideal input. And I can't draw it very well, but I swear I would draw it better if I was using my Apple Pencil. And it also means that the diode isn't going to turn on exactly when the input signal crosses 0. That's not when the diode is actually going to turn on or off. It's going to wait until there's 0.7 volts across it, and that's when it turns on. So it turns on at 0.7 volts. There's a little delay, right? And at the very top of the cycle, the peak voltage is going to be 0.7 volts less. It's going to be 0.7 volts less everywhere, all through that sinusoid. I should also note that we can put the diode in the other way, and instead of having the positive going, I should stop complaining about not being able to get this little pencil thing, this little pen to highlight. But I know you're sitting there waiting for me to do something, and I'm madly trying to do something, so I always feel obligated to tell you I'm trying to do something and it's not doing it. So the regulator, or the rectifier we looked at first, picked up the positive going peaks, but if we put the diode facing the other way, then we'll get the negative going peaks, right? And so we'll have a signal which is only negative, and we'll have a signal which is only positive, the positive peaks being here, right? And the negative peaks being here and here. So when the output is going high, the other peak is 0 if we have another diode. We could use two diodes, one facing one way and the other facing the opposite way, and that's leading us to how we can get a full that kind of full rectification of both halves of it. If we can build two separate circuits, one that gets the positive half, one gets the negative half, and then add them together with one of them being inverted, then we'll have it. And it's fairly straightforward to do that.